Today I'm excited to talk a little bit about a technique that we use to measure the energy of chemical reactions or to get at some of the kind of energy or thermodynamic properties of materials, such as things like the heat capacity or the specific heat. And so one of the ways that we can do that is with a technique called calorimetry. And the word itself tells you exactly what it is, which is often kind of the case with some of these scientific terms that have roots in Latin and other cool languages. So calor or calor comes from heat. So think in French, calorique means heat. In Spanish, if you're talking about how warm it is outside, you would say hace calor. And so it's the same kind of root. Metry, of course, refers to measurements. So we are measuring heat. And the way that we're doing this is with a setup that can be done with something as simple as a coffee cup, which is just kind of neat. So the setup that I'm going to kind of show, and with my traditional amazing art skills here, is essentially a coffee cup setup. And we're going to be able to measure, in the first example, we're going to look at the specific heat of an unknown metal. So I found a chunk of unknown metal. I want to find out what it is. How would I go about doing that? Well, one of the ways is I can measure the specific heat of it, and then I can compare that specific heat to certain known metals, and then I can determine its identity. That would be one way to go about doing it. I could also measure a chemical process, so I could dissolve a substance in here, and we'll do an example with that in this video as well, and then see how the solution's temperature changes as that reaction goes to completion, and that will give me some information about the delta H, or the enthalpy of that process. So calorimetry is really powerful, and it's kind of cool that we can do it with such common household sort of items. So if you have a thermometer and a couple coffee cups, then you have a calorimeter, which is kind of neat. Okay, so here's how it works. If we have water in our calorimeter and we have a specific mass of that water, so let's say, for example, that we have 50 grams in here. So I have 50 grams of water. I know the specific heat of water. That's something that's pretty well known to me. So that 50 grams of water with that specific heat, and that water is going to act within my calorimeter so long as I can insulate it from the outside, right? So if I have one of those really heavy-duty styrofoam, bad for the environment kind of coffee cups, those are going to help to keep all the heat inside. So that water is going to act as my surroundings for whatever system I'm going to stick in there. So if I start off with my water at kind of normal room temperature, right? So let's say that the temperature of my water just under normal conditions here in my apartment is 22 degrees Celsius. Then if I take some metal, right, then with my water, I have mass, I have a specific heat, and I have a temperature. So now if I have a temperature change, I can calculate the heat of a reaction, right? So that's kind of the key to all of this is this equation here. My Q is equal to the specific heat times the mass times the change in temperature. So I have almost all of the key components to that with my calorimeter. I just need something that's going to change the temperature, and then I need to be able to relate those two items. So let's say I have a chunk of unknown metal, and let me heat that thing up a little bit. So let's say that I heat up the temperature of my metal to, let's say 98 degrees. So my metal is at 98 degrees Celsius. Let's get myself another sig fig here. 98.0 degrees Celsius. So I've heated up the temperature of my metal, and now I have mass. I know what the mass of my metal is, so I weighed it out on a balance, then I heated it up, and now I'm going to stick this thing into my calorimeter, and I'm going to put a lid on it, right? So now I have my chunk of my metal in here. That's pretty good. It's obviously a chunk of metal. All right, and now I'm going to put, a lid over this thing, but still be able to see my thermometer. And so if I have an insulating lid on top of this thing, now my metal is at 98 degrees Celsius. That's what it started out at. My water is at 22 degrees Celsius. So what's going to happen? Well, the temperature of my metal is going to go down. So T of my metal is going to go down, right? Because it's going to get cooler. The heat always moves from the hot thing to the cold thing. the temperature of my water is going to go up as it is absorbing that heat, right? So my metal's starting to cool off, my temperature of my water is starting to heat up, and at a certain point, and you guys kind of know this intuitively, at a certain point these things are going to reach some sort of equilibrium or equilibrated temperature, right? So they're going to reach the same temperature. So they're going to have a final temperature of somewhere in the middle between the two, something greater than 22, but less than the 98. So if I look at my thermometer there, at the end of this reaction, then let's say that it ends at 45 degrees Celsius. So that would be kind of the hottest point that the water reaches before it starts cooling back down, if we're thinking logistically about what we're measuring here with my thermometer. So this is just kind of logistically what's going on, what's happening in the lab. I have an initial temperature of a metal, I have initial temperature of water, I have a mass of both my water and my metal. I know the specific heat of my water, and I'm trying to figure out what my metal is. So what I'm really searching for is my specific heat of my metal. So how would I go about finding that? Well, what I know is that if my water is my surroundings and my metal is my system, then my metal is getting cooler, and therefore the heat is coming off of it, right? So if we're thinking about this in thermodynamic terms, that heat from the metal is being released from the system into the surroundings. So in terms of convention, we would say that that's negative. Now that the amount of heat that the metal loses, so heat metal releases, has to be equal to the amount of heat that the water absorbs. So I have to absorb some heat from my water. And we know that one is equal to the other if I have a closed container in a closed environment, if I did a good job with my coffee cups here, right? So I'm not losing a bunch of heat to the environment. Law of conservation of energy says that the amount of heat that is being transferred out of the system has to be the same amount of heat that's being absorbed by the surroundings. Okay. All right, so this relationship then, and I'll write this here at the top over here so I have a little more space. So this relationship, this negative Q of my metal, so the heat that my metal is losing is equal to the amount of heat that my water absorbs. Well, I have expressions for each of those, right? I could say that that Q here is equal to the specific heat of the metal times the mass of the metal times the change in temperature for the metal. And if I take the negative value of all of that, then that has to be equal to, and then we're going to kind of expand this guy out, the specific heat of my water times the mass of my water times the change in temperature of my water. Okay, so far so good on the logic. Now we have all of these component pieces. If we kind of go back to our diagram, I have a lot of these pieces and parts to fill it in. The only thing that I was really missing was the specific heat of the metal, and that's what I can solve for. So if I rearrange my equation right off the bat to solve for the specific heat of the metal, then I'll end up with this. There's the specific heat of my water times my mass times the change in temperature. And we'll kind of get into the signs and how this all looks when we get some numbers in here. Divided by the mass of my metal times the change in temperature of my metal. So all I did was just a little bit of algebraic rearrangement here just to get specific heat of metal by itself. And remember that specific heat is always going to be a positive quantity, so if I have some weirdness with my signs along the way, that's one way I can check that, right? If I end up with a negative specific heat, then I know I messed up somewhere. Okay, so I was given all these values, so I can just kind of plug and chug. My specific heat of water is that 4.184. Units on that are joules per gram degrees Celsius. My mass of my water, we said we started with 50 grams, coming from our original diagram. And the change in temperature of my water is final minus initial. So we said that the T final for both was 45, and the initial temperature of my water was 22.0, right? It was kind of room temperature. So if I look at this delta T, I can see that this is going to be a positive quantity, right? Because I increased in temperature, so my final minus initial is going to give me a positive value. Now when I divide that by my metal here, my mass of my metal, I had 201.5 grams. And my delta T for my metal then is final minus initial. So I have my final temperature, which again was the same for both because we got to that same equilibrated temperature. And it started at 98. So we can see that that delta T is going to give me a negative value, right? I started with a higher temperature than I ended with, so I have a negative value here. And when I take the negative of that negative value, when I multiply through, that'll give me a positive number. So I'll have a positive number divided by a positive number, which will give me a positive specific heat, which is what I'm looking for. And then when I plug in those numbers, then I end up with 0.451 joules per gram degree Celsius. And then I can go to a chart and I can actually look things up, and I would find that this is kind of closest to iron, for example, which is Fe on the periodic table. So I found a chunk of metal somewhere, figured out did a little, at-home experimentation and figured out the specific heat. So that's one way to do that. Now another application of a calorimeter and calorimetry is using that same kind of setup. I could also find information about the heat of solution. So I have my coffee cup, and instead of putting metal in there, I'm going to dissolve a sample of KCl. So potassium chloride is a salt, so that solid would dissolve. It's quite soluble. And now I have a solution that is made up of my salt and the water, and I can measure the difference in temperature. It started at 31 degrees Celsius when I put the salt in, and then it went down, that decreased the temperature, to 21.6 degrees Celsius. So we're going to calculate delta H, and recall that delta H is equal to Q. So if we calculate Q for this, then we have our specific heat times our mass times our change in temperature. Now with solutions, especially with ones of very small molar concentration, so this one's significantly smaller than a mole, then the specific heat can be the specific heat of water. And usually problems will tell you that the solution can be, you can assume that we're using the specific heat of water. This one didn't in particular, but it's such a small quantity that the water's specific heat is going to be the more overriding factor. The mass is going to be the total mass of the solution, so we're going to add those together, the 12.8 grams plus my 75 grams. And then my change of temperature is final minus initial. So we're going to have my final temperature, which was lower, my initial temperature. So we can see then that my Q, the heat from this, is going to be negative, right, because of the negative delta T, which means that heat is being released, which makes sense because it's getting cooler. In order for it to get cooler, the heat has to go somewhere, so it's going to leave the system. So my heat here, when I plug in my numbers and plug and chug through here, I got 3,453 joules. Now it asks for delta H in kilojoules per mole, so let's just do a quick little conversion to kilojoules here. I know that there's 1,000 joules in a kilojoule, so that's going to give me 3.453 kilojoules released, and again releasing indicated by my negative sign. And now I just need to calculate my number of moles. So I have 12.8 grams, use my molar mass, and I end up with 0.172 moles. Now I take my kilojoules divided by my moles, and I end up with a delta H of negative 20.1 kilojoules per mole, which means that it's exothermic. So I used my calorimeter. This is another way I could go about doing it. I divided my energy or my heat by the amount that I used, and then that gave me some information about this chemical process. So another important application of calorimetry. And as always, if you have any questions on this, don't hesitate to reach out. Otherwise, I will talk to you again soon.